There are two tests involved in identifying a critical point, whether it's a maxima or a minima. Check how these examples' critical point was categorized here in differential calculus. What are parametric equations? These are equations or functions which are written as a function of another variable. For instance, we have x as a function of t, and y also a function of t. The variable t is called parameter, and in parametric equations, the usual parameters used are t and theta. Let's have an example. Say x is equal to t, then y is equal to t squared. Let's use a table to find values of each variable. Take note that t is the independent variable, and both x and y are the dependent variables. Assuming t of -3, x turns out as -3, and y is 9. When t is -2, x is also -2, and y is 4. At t of -1, x is -1, and y is +1. At t of 0, x is 0, and so is y. Then when t is 1, x and y are also 1. At t of 2, x is 2, and y is 4. And if t is +3, x is 3, and y is 9. Connecting the dots in the Cartesian plane, we can identify the curve. So what exactly should we do to sketch curves from parametric equations? First is to take the first derivative dy with respect to x, after which we equate this ratio to 0 in order to identify t, which in turn should be plugged into the individual parametric equations in order to identify the critical points. After learning the important points, we then distinguish if they are the highest or the lowest extremes on the curve, and that is done by taking the second derivative of y with respect to x, which would be checked with the following conditions. First, if the second derivative is less than 0, or say it is negative, the critical point is a maxima. If y double prime is more than 0, the critical point is a minima. And yet, if the second derivative turns to be 0, or there is no clear answer, that means that the second derivative test failed. And if this happens, we can always revert back to the first derivative test. The parametric equations for the second example are x of t cubed plus 7 and y of 6t squared less 1. The critical points are taken by solving for the first derivative, dy over dx. But since parametric equations have another variable involved, solve for dx over dt and dy over dt first. From x of t cubed plus 7, take the derivative with respect to t, where dx over dt then becomes 3t squared with dt over dt as the derivative of the first term. Then there is also the derivative of 7, which is taken as 0. dt over dt is 1, simplifying dx over dt as solely 3t squared. For the second parametric equation, y of 6t squared minus 1, take the derivative with respect to t, giving dy over dt as the constant 6 with the derivative of t squared, which is 2t. Then attach dt over dt from chain rule. Then subtract the derivative of 1, which is taken as 0. dt over dt is 1, so dy over dt is reduced to just 12t. With these two parametric derivatives, take the ratio, making dy over dt upon dx over dt, That is 12t upon 3t squared. The dt's cancel out, and 12 and 3 are also reduced, bringing about dy over dx of 4 over t. After identifying dy over dx, we equate the slope to 0, thereby having t of 0. Knowing t as 0, we can now find the coordinates of the critical point. That is done by plugging in t in the original parametric equations. From x of t cubed plus 7, substitute 0 for t, making 0 cubed plus 7, or that is x of 7. Repeat the procedure for y, which is 6t squared minus 1. Substituting 0 for t, we get 6 times 0 squared minus 1, which gives y as negative 1. So the critical point is located at 7, negative 1. The next thing to do is to describe if the critical point is the highest or the lowest point from the curve. This is done by taking the second derivative of y with respect to x. So far, what we got is dy over dx, which is 4 over t. When we differentiate this equation, we do it with dy over dt in order to simplify the right term, but by doing so, the left term becomes the second derivative of y with respect to t and x. Moreover, instead of using quotient rule, which is admittedly longer, let's place a negative reciprocal, making the term 4t raised to negative 1. Differentiate and keep the constant 4 with the old exponent of negative 1, and the term t raised to negative 2. Then attach dt over dt as required from chain rule. Dt over dt is 1, so the second derivative of y with respect to t and x becomes negative 4 over t squared. Now eliminate dt and adjust dx by multiplying it by the reciprocal of dx over dt. We just computed dx over dt as 3t squared, so take its reciprocal of 1 over 3t squared and multiply it to the derivative. This then is simplified as negative 4 over 3t raised to 4. Now key in t of 0, then work with the standard conditions. The second derivative of y with respect to x then is negative 4 over 3 times 0 raised to 4. Having a 0 denominator makes the function indeterminate. This shows that the second derivative test failed. So we have to revert back to the first derivative test to identify concavity. The dividing line is at t of 0, so we can assume t of negative 1 on the left. Take dy over dx of 4 over t and plug in t of negative 1, which makes the slope dy over dx as 4 over negative 1, simplified as negative 4. This says that before t of 0, the slope is negative, which starts at top left and slides down to the bottom right. Now assume t of positive 1 on the right side of the line. Dy over dx then becomes 4 over 1, which is positive 4. A positive slope starts at bottom left and rises to top right. From the characteristics of the slopes, we can then deduce that the critical point is a minima.